Inside the Heliflow heat exchanger are the coil, the manifolds, the casing, and the base plate. Copper is the standard tube material of the Heliflow, but the tube bundle can be built in a variety of materials, including stainless steel, Admiralty, cupro-nickel, and titanium. You can also specify the shell side material to be compatible with your process. The standard material is cast iron, but options include cast, fabricated or stainless steel, or more exotic materials. The standard connections for the Heliflow heat exchanger are NPT with a male tube side connection and female shell side connection. Alternative connection options include flanges, butt weld, Victolic or other special fittings. In a cross-sectional view, on the tube side, fluid flows into the center manifold and then takes the flow path to the outer manifold and discharges out of the outer manifold. On the shell side, the fluid enters just to the right of the outer manifold and flows in the opposite direction of the tube side fluid. The fluid exits just to the right of the center manifold. You can see the hot side fluid inside the tubes and the cold side fluid outside the tubes in the shell side. These fluids can be reversed with the cold fluid inside the tubes if that's what the application requires. The design of the Heliflow heat exchanger enables 100% true countercurrent flow. The spiral tube path further enhances heat transfer due to increased beam number. We provide close temperature approaches, typically within 5 degrees Fahrenheit of the opposite fluid. Temperature crosses are also possible, unlike many heat transfer technologies. Since we have 100% effective surface area, there are no LMTD correction factors. These combined thermal advantages give us a heat transfer rate approximately 40% greater than a traditional straight shell and tube. The spiral flow path of the Heliflow ensures that you get turbulent flow. Low flow rates that occur in a straight shell and tube design can cause poor velocity and result in laminar flow. With the Heliflow design, you get an eddy effect, constantly turning the fluid over as the fluid travels through the coil, ensuring a consistent turbulent flow path. Heliflow's eddy effect also creates a higher shear stress at the flow boundary. Both advantages greatly reduce fouling rates. Instead of sizing the Heliflow based on a fouling factor, we use a cleanliness factor. We typically size our Heliflow heat exchangers with at least 15% excess surface area. Imagine a high-pressure gas cooling application with a requirement to cool 90 pounds per hour of helium gas at 3500 psig from 117.5 degrees Fahrenheit to 50 degrees Fahrenheit using 2.5 GPM of ethylene glycol at 40 degrees Fahrenheit. When you compare the Heliflow heat exchanger to a standard shell and tube heat exchanger, you see that the Heliflow requires much less surface area than the shell and tube. The Heliflow, 2.5 square feet, is much smaller than the straight shell and tube, 24.87 square feet. Looking at the heat transfer rates and the basic heat transfer calculation, Q equals U times A times LMTD, you can see why the resulting surface area is much less for the Heliflow. Now imagine a mechanical seal cooling application with a requirement to cool 2.5 GPM of seal water from 300 degrees Fahrenheit to 180 degrees Fahrenheit using 3 GPM of water at 75 degrees Fahrenheit. When you compare the Heliflow heat exchanger to a standard shell and tube heat exchanger, you see that the Heliflow requires much less surface area than the shell and tube. The Heliflow, 2.5 square feet, is much smaller than the straight shell and tube, 13.6 square feet. Looking at the heat transfer rates and the basic heat transfer calculation, Q equals U times A times LMTD, you can see why the resulting surface area is much less for the Heliflow. In both these cases, the heat transfer rates are much larger in the standard shell and tube heat exchanger, and the velocities are much lower than the Heliflow. This results in a lower heat transfer rate, which ultimately increases the surface area requirement. The true cost of any heat exchanger is based on price per square foot. The compact design of the Heliflow is the much more attractive option to your bottom line. COIL design allows the Heliflow to handle pressures up to 15,000 psig on the tube side, and the unique manifold design eliminates the need for any gaskets on the tube side. On the shell side, the Heliflow can handle pressures up to 5,000 psig. The unique spring-like coil eliminates the concerns of thermal expansion and thermal shock. The coil can expand and contract within the housing and eliminate the need for an expansion joint or thermal fatigue that you would normally find in a traditional shell and tube heat exchanger. One key feature of Heliflow heat exchangers is that you can gain access to the shell side without disrupting the piping. You just unbolt the casing from the base plate, remove the back side of the casing, and then you have access to power wash or clean the shell side. Our standard coil spacing is typically 1/8 inch to 1/4 inch, depending on model size, but these dimensions can be varied. If a high flow rate on the shell side is present, we can widen the coil spacing to provide a reasonable velocity through the shell. If we have a low flow rate on the shell side and need to increase velocity, we then tighten the coil spacing up to 1/16 of an inch if needed. One of the most common options for the Heliflow heat exchanger is a 3-pass design for vaporizing applications. For a 15-tube unit to function properly, the first pass comes in, and a baffle plate inside the manifold forces the fluid to the outer manifold between tubes 5 and 6. The outer manifold has a baffle plate between tube 10 and 11, which deflects it back to the inner manifold. This ensures the fluid takes 3 passes through the heat exchanger before coming out to the outer manifold and back to process. A drop tube design functions similarly to the 3-pass reverse manifold design, except that the fluid comes into the bottom 5 tubes through a drop tube in the outer manifold. The fluid flows to the inner manifold and back through the next 5 tubes. The inner manifold has a baffle plate between tubes 10 and 11, which ensures the flow through the second pass back to the outer manifold. The fluid then diverts back to the inner manifold, making the third pass through the Heliflow and then out and back to process.